The manufacture and decoration of the two-piece beverage can is a complex operation which requires several specialist processes to complete. The modern beverage can is made from two parts, the body and the easy open end. The body has a domed bottom, a sidewall and a necked and flanged top. The lid, or end, which starts out as a plain end, is converted into an easy open end by the addition of a stay-on tab. Crown Bevcan Europe and Middle East produces a full range of cans that can suit all consumption occasions from 15 centilitres to 50 centilitres. The process involved in producing the finished can body is a two-stage operation, separated into the front end and the back end. The front end operations are coil handling, body forming, trimming and washing. The back end operations include coating, decorating, spraying, necking, flanging and finally testing and palletizing. Can bodies can be produced from tin plate or aluminium. In this video, we'll concentrate on aluminium coil as the primary material. The coil stock is produced from a combination of aluminium ore and recycled material. The molten aluminium is brought to the right temperature in a furnace. Once the aluminium is cast, it's transported to a rolling mill, where the material is progressively rolled thinner. Once it's reached a critical size, it's coiled and moved to the next process. This machine rolls the metal to its final required size for can making. The aluminium is then washed to remove any dust or oil. The average width for aluminium coil is 1.5 meters and its length is around 7 kilometers, producing on average 700,000 cans. Coil stock is delivered and stored with its coil vertical until required. Each coil can weigh as much as 12 metric tons, and damage at this stage would cause problems in manufacture. So every care is taken over its handling. At the front end, coil stock enters the line via the coil handling operation. First, a coil is loaded into the down ender. The function of the down ender is to turn the coil through 90 degrees and position it onto the coil car. Then, the coil car loads the coil onto the expanding shaft or mandrel of the coil dereeler, ready for use. The speed of the dereeler is governed by an automatic speed control system to ensure that the feed rate matches that demanded by the cupping press. From the dereeler, the coil is fed into the lubricator to prepare the aluminium for the first press operation. The process of drawing the material into seamless containers is a precise operation, so the correct ratio of lubricant to water is essential to avoid the material tearing and to ensure the cups and cans are formed within specified tolerance limits. From the lubricator, the coil is fed into the cupping press. In a double downward stroke, small circular discs called blanks are cut and then drawn into a shallow cups shape. The tooling for this process consists of outer tooling that cuts out the blanks and a punch which pushes them through an inner die or mold, drawing each blank into a cup shape. At this stage, skeletal scrap is generated and removed by a vacuum scrap system, baled and returned for recycling. From the cupping press, the cups are taken by a mass handling system to the body maker machines. A single cupping press feeds several body makers. The body maker takes the cups and forms them into bodies. This is done using a ram to push the cup through a set of rings. The cup is first reduced in diameter and then forced through a series of wall ironing rings. These rings are slightly smaller, so the walls of the cup are squeezed thinner. The metal that's displaced has to go somewhere, so that means that the height of the cup is increased until it's slightly greater than the finished can. Finally, at the end of this stroke, the base of the can is formed by the dome station. A great deal of heat is generated in the process, so the tool pack is fed a constant supply of coolants mixed with lubricants. This is supplied by a filter and recirculation system that removes debris collected from the process. On exit from the body makers, the can body is oversized and has an uneven top edge, so it's passed directly into the trimmer. Approximately ½ an inch or 12 millimeters is trimmed off, and the can emerges at the required height and with a clean top edge. The condition and alignment of the trimming knives is critical, as imperfections on the can now could cause problems in the latter stages of manufacture. From the trimmer, the cans are conveyed and inverted into the can washer. The purpose of washing the cans is to remove the lubricant and any small particles of aluminium called fines which accumulate during the body maker process. During the washing process, a combination of water, hydrochloric and sulfuric acids are sprayed onto the inverted can. After rinsing with clean water, a bonding agent is sprayed onto the can. This prepares the can surface to receive external and internal coatings. Before being dried, a mobility enhancer is sprayed onto the can, reducing the surface friction of the cans to improve both the drying process and downstream can handling. The water needed for washing the cans is taken from the local water supply and treated to meet the high standards required by the washer process. Wastewater from the washer must then be processed through a water treatment plant, ensuring that discharged water conforms with local regulations. This completes the front end of the two-piece can making process. Acting as a balancer or buffer to control the flow of cans from the front end to the back end of production, there's a palletizer-depalletizer known as a PDP. This helps maintain optimum production capacity of the line by temporarily storing cans if production should slow or cease at the back end. When back-end production has restarted, the cans can be reintroduced into the line as and when required by reversing the operation. The trimmed, dried and clean cans are fed into the coating machine, which applies a base coat, usually white, to the outside of the can. The coating provides a base color for subsequent decoration and external protection of the outside of the can wall. A lacquer coating is applied to the can base by the base rim coater. The purpose of the base rim coating is to protect the base from corrosion and to reduce friction between the conveyor and the can. This helps the high-speed transfer and filling operations. The cans are transferred to a peg chain, which carries them through a peg chain oven to dry and cure the coatings. The decorator prints the customer's design in up to 6 colors onto the can. The graphic design is transferred onto the can by printing each color from individual printing blankets. If required, a design can be protected by application of over varnish, which also reduces friction and improves the movement of the cans. Good quality ink, a mixture of synthetic resins and organic pigments, and accurate machine settings are essential for high-quality printing. According to the customer requirements, the base of the can could receive a second application of lacquer. The cans are then carried through the decorator's peg oven to dry and cure both the inks and the base rim coating. Visual checking is made easier by looping conveyors at low-level inspection points. The decoration operations on the back end are now complete. Next, the cans are passed on to spray machines to be sprayed internally with a coat of lacquer. The cans are rotated in a vacuum turret to make sure the inside surface is fully and evenly coated. The lacquer provides an effective barrier between the can and its contents. If left uncoated, the result could be an off taste or even corrosion. An internal bake oven dries the internal lacquer. The cans are then waxed with a fine lubricant before die necking. This operation reduces the diameter of the open end of the can. Once the neck has been formed, the can is then transferred to the spin flanger. This forms a flange at the top of the can neck that will enable an effective seal to be made with an end after the can has been filled. From the spin flanger, the cans are passed through the light tester to check for split flanges or pinholes. Cans pass through a low-intensity light source. Any can emitting light is rejected. There's further online quality control with a vision inspection system. This is an internal inspection of the can using a video camera coupled to a computer capable of recognizing defects on the inside of the can. Any can with a visual defect is automatically rejected. The can bodies are now conveyed to the palletizer to be packed, ready for transportation to the customer. A palletizer packs the cans in the tightest, most effective pattern. This is to minimize the volume and the risk of damage in transit. On discharge from the palletizer, the fully loaded pallet is strapped and stretch-wrapped for protection. Pallets are transported either to warehouse storage or direct to the filling plant. At the filler, the pallets are unloaded and directed onto a depalletizer. With strapping and stretch wrap removed, the cans are taken off a layer at a time from the pallet onto the mass handling conveyor. The cans only receive a short water rinse before entering the filling machine, so cleanliness in the manufacturing plant is most important. The filling machine has filling heads mounted on a rotating turret. Empty cans are filled as they rotate around the machine. The speed and size of the filling machine is related to the production requirements. The can is then transferred into the seamer, where it receives an end. The name seamer comes from the process of attaching an end to a can. The double seaming process folds the curled edge of the end around the flange of the can. This provides an effective hermetic seal. At the end of the filling line, the cans are conveyed to the wrapping station to be packed. The packs are then transferred to a warehouse or delivered to the customer. From there, the cans follow their route through the retail chain before arriving in the store, on the shelf, ready to be purchased. Once used, recycling puts the metal back into the system, and before long, you could be using that very same metal again. Approximately 220 billion cans are consumed around the world every year. Produced and filled at speeds of 2,000 cans per minute, light, convenient, chillable, and unrivaled system economics and product protection, the beverage can is the ideal single-serve pack for fillers and consumers.